let's go ahead and look at solving an equation like this. Tangent inverse cosine of square root of 2 over 2. And this up here about the inverse trig functions will come into play here in a second in a few examples. So what we do is we start on the inside of these. So let's go ahead and start on the inside. So on the inside, this means what angle in the restricted region 0 to pi, points inclusive, has a cosine of square root of 2 over 2. That's the question. Well, we know this. This is going to be pi over 4. And you know this because you know your unit circle. And then what we do is we take this value of pi over 4 and we plug it back in here. And we end up with, okay, what is the tangent of pi over 4? And of course we know the tangent of pi over 4 is positive 1. Pi over 4 lies in the first quadrant. So that works pretty slick. Let's go ahead and look at another example where it might not be a value off the unit circle, but I can still solve it. And this might look familiar from our review quiz we had towards the end of towards the beginning of the semester. So this will look like the cosine of the inverse sine of 5/13. Okay, 5/13 does not look familiar to me. This is not a standard angle value. So from here, this is asking the question, what angle in the interval negative to positive pi over 2, points inclusive, has a sine of 5/13? And instead of saying I have no idea, let's go ahead and say theta. So what we have here then is a right triangle. Always mark your right angle. We have some angle theta, and it doesn't matter which angle you mark as theta as long as when you write the sine of theta, remember sine is opposite over hypotenuse. So what this is saying up here, this question, and because I said the answer was theta, the sine of theta is 5/13. Now of course we can use Pythagoras Theorem here to solve this. To solve for this unknown side, that will be opposite over hypotenuse. This would be adjacent, so I'll call it A. A squared plus 5 squared is equal to 13 squared. Using Pythagoras Theorem, A squared would equal 169 minus 25. A squared is 144, so A is 12. It's actually plus or minus 12, but we'll see here in a second how this will fall out in terms of positive and negative values. Okay, now from here I've said, okay, I've got this triangle figured out. I said my answer was theta, so let's take this value of theta and plug it back in here. So the cosine of theta then is what I'm looking for. Well, remember, cosine from SOHCAHTOA is adjacent over hypotenuse, so I get 12/13. So that's what we're looking for here. So if you think about the inverse sine, let's go ahead and have our little conversation about the positive and negative values. If you think about the inverse sine, I have to either be, remember I'm between negative and positive pi over 2, I'm in the first or fourth quadrant. So whatever I got for this answer, inverse sine of 5/13, okay, I got theta 4. Now this says, what angle between negative and positive pi over 2 has a sine of 5/13? Well, if sine is positive, that means I have to be up here in my first quadrant. And the cosine of a first quadrant angle is positive, so that's why I end up using the positive value here. So you kind of have to keep track of those even for a non-standard angle that you'll be working with. Let's go ahead and look at another example. And again, knowledge of your unit circle here is absolutely crucial. Let's go ahead and look at the example of the secant of the inverse tangent of 3x. Okay, so we start with and we say, okay, what does this mean? Inverse tangent of 3x means what angle in the interval negative to positive pi over 2, and again, these are not inclusive. These are parentheses, not brackets. And now remember, these are points inclusive, or not inclusive, they're exclusive. So I have parentheses, not brackets, has a tangent of 3x. And of course your response is, I have no idea. So we just say theta, or use your other favorite Greek letter there. And so we plug in this value of theta, and this is actually saying, okay, then the tangent of theta is 3x. So we draw our right triangle. Use our good old SOHCAHTOA again. I guess first of all we ought to use tangent of theta equals 3x is the same as 3x over 1. So that's opposite over adjacent. And now this is the hypotenuse that I'm trying to solve for. So I know that leg squared plus leg squared, and of course this is 3x quantity squared, equals hypotenuse squared. So solving for hypotenuse squared, I get 1 plus 9x squared. The hypotenuse then is the square root of 1 plus 9x squared. Now don't make the mistake here and distribute the radical and say, oh, that's 1 plus 3x. Remember, we can't distribute a radical across a sum or a difference. So now we take this information, and remember I said my answer here was theta, so I stick theta in here. Secant of theta is what I'm looking for. Well, secant is 1 over cosine. Cosine of theta is adjacent over hypotenuse, and remember our hypotenuse was root 1 plus 9x squared. And so for the cosine of theta, it's kind of messy. For the cosine of theta, I'm going to have 1 over the adjacent leg, which is 1, over the hypotenuse, which is root 1 plus 9x squared. But when you divide by a fraction, you multiply by the reciprocal, so the 1 plus 9x squared flips up top, square rooted, over 1. And that is my solution. So you can use these inverse trig functions quite a few different ways, but you should be able to work some pretty intricate patterns here working with those. Let's go ahead and look at another example. In this next example, we're going to be looking at the inverse tangent of 2x equals -1. And the key here is to solve for x. Well, to get the 2x out of the argument of the tangent function, we need to take the tangent of both sides. So, because of this idea that we talked about up above of inverse trig functions, if you keep track of your restrictions, the tangent of the inverse tangent of 2x is just going to be 2x. But let's look at that just a little bit. This means what angle in the interval negative to positive pi over 2, points not inclusive, meaning I have parentheses, has a tangent of 2x. And remember, we're going to say, well, theta does. Well, this means that the tangent of theta equals 2x. Okay. Well, that's what this is asking us for right here. Remember, I replaced this entire statement with theta. And so this means tangent of theta. Well, I just answered that the tangent of theta was equal to 2x. So what ends up happening is this boils down to 2x equals tangent of -1. Now divide both sides through by 2, and we have x equals the tangent of -1 over 2. Now do not be tempted here to say, oh, I know what angle has a tangent of -1. It's negative pi over 4. This does not say inverse tangent, just this says the tangent of -1. This means the tangent of -1 radians. This is an exact value. We don't need to do anything more than this. This is our solution. We can't do anything else with that. So that's some examples of working with inverse trig functions. Now, inverse trig functions also has a nice little set of derivatives. Now, the derivatives of inverse trig functions definitely need to be memorized. Let's go ahead and start, and these are going to be slightly different than the book. The book doesn't use substitution yet. It doesn't use a chain rule. It just uses an argument of x. And in order to kind of move up a little bit quicker, let's go ahead and look at this in terms of the arguments of any generic function instead of just x. Let's look at the derivative with respect to x of the inverse sine of u, the derivative with respect to x of the inverse cosine of u. Let's put that one over here. Derivative with respect to x of the inverse tangent of u. Derivative with respect to x of the inverse secant of u. Oops, inverse secant of u. Derivative with respect to x of the inverse cotangent of u. derivative with respect to x of the inverse cosecant of u. And I think that's our last one. Okay, the derivative of the inverse sine is going to be 1 minus u squared square rooted in the denominator over u prime. Tangent, and this is going to be one of the most common ones we look at, is u prime over 1 plus u squared. Inverse secant is going to be u prime over the absolute value of u times the square root of u squared minus 1. Inverse cosine is going to look almost the same as the inverse sine derivative in the denominator, but the numerator is positive. And remember, these are prime marks, they're the derivative of u. Negative u prime for the inverse tangent, 1 plus u squared. So you can see these match pretty close. They're a difference of a negative. Negative u prime over absolute value of u squared minus 1, square rooted. Okay, so those are some common derivatives. And again, these will definitely need to be memorized. And you should also remember the domain and range restrictions for both the functions, all these trig functions, and their inverses. So let's go ahead and look at a few problems. Let's look at finding the derivative of f of x equals the inverse sine of x squared. F prime of x is then going to be a matter of identifying our u. So in this case, u would equal x squared, and then u prime, which is the same as du, of course, is 2x. So what we could do here then is look at our form. Our general form for the derivative is going to be the derivative of u over the square root of, and again, scroll up just real quick and you see it's 1 minus u squared. Okay, so our u prime was 2x over the square root of 1 minus x squared. And that's my derivative. The slope of the tangent line at any point along the graph. Okay, so this works pretty slick. Let's go ahead and look at another example of derivatives. Let's look at the function f of x equals, let's do one a little bit more complicated, x inverse tangent of 2x. Okay, so first of all, we see we have a product of values here. We have two functions. So I'm going to be using the product rule to find the derivative. Okay, so derivative will be the first function times the derivative of the second function plus the second function times the derivative of the first function. And of course, some parts of these are a little bit easier than others. Okay, but for the most part, nice little product rule. So let's go ahead and get started here. The first function, of course, is easy enough to work with, x. Now the second function, again, you need to look at your u here is 2x. U prime, or du, is 2 then. So when we have our derivative in this case, I have u prime, which is 2, over 1 plus u, which was 2x quantity squared. Okay, and then if you need to, run up top and double check it against these formulas, but you need to have these memorized. Plus inverse tangent of 2x, okay, times the derivative of x, which is 1. And I'm just going to put that 1 in. We don't really need it for anything, but I'm going to leave it in the expression so we can see that the derivative was taken. And then let's kind of clean this up again. We have 2x over 1 plus 4x squared plus the inverse tangent of 2x. And that's my derivative. And again, it's going to be really important to have these memorized because very soon what we're going to be doing is looking at antiderivatives.